Okay, so now we are getting to question 2. And in question 2 this is the force question. It's usually like that. It's the Newton law question is the first question after the multiple choice, and it's usually an object on an incline, or the two boxes on a slope, or usually something about two objects with tension between. Not always, but very often that's the type of question in as your first question. We have two objects, a 5 kilogram and a 2 kilogram, and they are linked by a light inelastic rope. It just means that we don't have to worry about the mass of the rope. They are pulled upwards on the incline of angle 30 degrees with the horizontal by a force F. Ignore the mass of the rope. The kinetic frictional coefficient of the 2 kilogram and the 5 kilogram objects are respectively 0.1 and 0.2. Write down Newton's second law in words. So let's quickly go through the laws. The first law, Newton's first law, is that an object in motion will stay in motion at or an object at rest will stay at rest, and it will travel at that constant, and it will keep its velocity unless an external force acts on it. So if there's no net force acting on an object, it will just either stay at rest or it will stay at a constant velocity it is traveling at. Point just being, the first law says that if something is at rest or at a constant velocity, there's no net force. All the forces act against each other, cancel out. So if there's a forward force, there's an equal and opposite backwards force, that kind of thing. That's Newton 1. Newton 2 then goes on and says, well, if an object is then experiencing a net force, it will accelerate. And if it is accelerating, then its acceleration is directly proportionate to the net force acting on it. So the bigger the net force, the bigger the acceleration. But it's inversely proportionate to the mass of the object. So the object is accelerating, but the bigger the mass is, the smaller the acceleration. The smaller the mass is, the bigger the acceleration. So again, Newton 2 is therefore that when an object is experiencing a net force acting on that object, it is causing the acceleration, it will cause it to accelerate proportional to the size of the net force, and inversely proportionate to the mass of the object. Newton 3 is that any force exerted has an equal but opposite force acting against it. Okay, so now question 2.2. How will the kinetic frictional coefficient be influenced if the angle between the horizontal and the incline is increased? The frictional coefficient. The frictional coefficient is only dependent on the surface material between the two objects. So the surface, the kinetic, so if it's ice and a cardboard box, it will have a certain kinetic coefficient. If it is a steel platform and a rubber box, it will have a coefficient, a specific coefficient. So it's got nothing to do with the angle of the slope, with the mass of the object. It's got to do with the surfaces that are touching. So what will the coefficient, what will affect the coefficient if the angle is increased? Nothing. It will stay the same. Okay, next is calculate the tension in the rope if the system accelerates at 4 meters per second up the incline. Okay, so we have to calculate the tension in the rope. Now, this is something I can just not get through to students. You must start with a force diagram. So we have two objects. Okay, here's my object one. Let me not, because I don't know how to turn that. So here's my two objects. Okay. Both of them are experiencing some forces. They're moving up the incline, so I'm going to change all my forces to be in the same direction or in the opposite direction. But first of all, there's a force F is the applied force. Okay? Then there's a rope connecting these two. Now this is Newton 3, that this rope connecting these two it's got tension in it. So for this object here, the tension is in this direction, but for this object, the tension is in that direction, because basically what this tension is doing, it is pulling the big object up the slope, but what it's doing for the small object, it's a drag pulling it down the slope. Okay, then both of them are experiencing friction. There's that one's friction, and there's that one's friction. Okay, and then both of them have weight parallel to the surface, so it's being pulled up the slope. Both of them also have weight that's parallel to the surface down the slope. So if I look at this whole thing, I'm trying to work out tension in the rope. If this object is accelerating upwards at 4 meters per second squared. Okay, so I have a choice. I can either look at the system as a whole, but when I look at the system as a whole, I won't have tension separate. Tension is a component inside the system. So I can't look at the system as a whole, because the system as a whole doesn't have tension externally. So look at this. If I combine this into one system, do you notice what are all the forces acting in here? Well, now tension is cancelling out. Tension doesn't have an effect on the whole system. It has an effect on the small mass and effect on the large mass. So I have to look at them separately. So here's them separately. Okay, probably the force applied is not known. I don't know how big the force applied is. So I either have to look at the top part, or I have to look at the bottom part. Now the problem with the top part is there's a force that's unknown, the force applied. So all I know is the only things I have complete knowledge of is all of the things acting on the bottom mass. So at what rate is it going up the hill? So I'm simply going to say, well, the net force is equal to mass times acceleration. And I'm only going to look at the bottom mass, because I have to separate into one of the two, and the bottom one I have more information of. Now the bottom one has a positive force pulling it up the slope. That's the tension. But it also has weight parallel to the surface that's pulling it in the opposite direction, and it also has friction. Okay, and there's always just these three forces in net force and in net work done. It's your applied force, your gravity, and your friction. Now there can be other things, of course, but these are the main ones. Okay, and then it's mass times acceleration. Now we have all of this. We have tension is what we're trying to find. Weight is simply mass times gravity times sine of the angle, the weight parallel to the surface, minus friction is worked out by taking the frictional coefficient times the normal force. Now the normal force for an object going up a slope is mass times gravity times cos of theta is equal to mass times acceleration. Now I've got everything. So tension minus, okay, so the mass, this is the mass of 5 kilograms, so it's 5 kilograms times 9,8 times sine of theta is 30 degrees, minus mu is now the frictional coefficient, the kinetic frictional coefficient on the 5 kilogram, which is 0,2, and then mass 5 times 9,8 times cos of theta, which is 30 degrees, times mass, which is 5 times acceleration, and they told us it's going up the hill at 4 meters per second. Okay, and there it is. All I'm going to do is solve t. So if I'm going to solve t, I'm just going to have this and these two things that's being subtracted are going to be added on that side. So first of all, my mass times acceleration, in other words my net force, is 20, 5 times 4, minus on this side is going to be plus 5 times 9.8 8 times sine of 30 is a half, but you can type it in as sine of 30, plus, again, because this on the other side will become a plus 0.2 times 5 times 9.8 times cos of 30, so 30 cos, okay, is equal to 52.99 newtons. Okay, 52.99 newtons, or 53 newtons if you got there. Okay, so that is the amount of force, sorry, that is the tension in this rope if it's accelerating at 4 meters per second up the incline. The tension in the rope can support a maximum of 70 Newton force before it breaks. If the force applied to the system is 100 newtons to pull the system up the incline, show by means of calculations if the rope will break. Okay, so very similar. This time I'm just working with the top part, and first I'm going to work out what is going to be the acceleration on, so I'm going to do the same calculation that I did here, but first I'm going to work out what is going to be the acceleration on the system if I apply 100 Newton force. Okay, so if I look at the system as a whole, what are all the forces acting on the system as a whole? Well, there's a applied force, okay, then there's the weight parallel to the surface of the 5 kilograms. There's also a weight parallel to the surface of the 2 kilograms. Then there's the friction of the 5 kilogram, and there's also the friction of the 2 kilogram. Now all of this will be equal to the mass, this is the total mass of the system, times the acceleration of the system. So what am I basically doing? Again, I'm trying to calculate the tension in the rope. To calculate the tension, I need the acceleration of the system. So that's why I start with the system as a whole, finding the acceleration of the system. Now every component in the system is accelerating at the same pace, so that's why I'm doing that. And so now when I substitute, I get the force applied is 100 newtons minus, and then this I basically calculated already up here, but that's 5 times 9,8. Let's do this. If I look at the system, I can just combine it. 5 plus 2 times 9,8 times sine of theta. Okay, that's just the system is 7 kilograms. The rest of it is the same, so you just take it out as a common factor. Well, pause the video and think that through if you need. But here we can't do it because they have different coefficients of kinetic friction. So you can, but then you still have a plus inside. So rather we'll just say substitute as is. So we'll say that the 5 kilogram had a 0.2 times 5 times 9,8 cos of 30, and the 2 kilograms at a 0.1 times 2 times cos 9.8 times cos of 30. And this was equal to the mass, which is 7 kilograms times the acceleration. So when we do that, we've got 100 minus 7 times 9.8 times 30 sine, okay, minus 0.2 times 5 times 9.8 times 30 cos, minus 0.1 times 2 times 9.8 times 30 cos. Great. And that gives me 55.55. I'm going to say memory store, and this is my, what is this? My net force. So my net force is 55,515 is equal to 7a. So my acceleration is equal to my net force divided by my mass. Okay, so that is divided by 7 is equal to 7.93. 7.93 meters per second squared. Okay, that's my acceleration. Now, once I've done my acceleration, I can do exactly what I did up here and work out this top. So I have this expression, but instead of having it equal to 5 times 4, I just have it equal to 5 times 7.93. So I'm literally going to write the same thing down. And okay, just to show you we have enough time, we're going to write down t minus 5 times 9.8. So this is my mass in the direction of the slope. This is my frictional force for the 5 kilograms. You could have now actually done it for the 2 kilograms as well. You could have chosen which one you wanted to do it on, but the 2 kilogram has more forces because it here has the applied force upwards minus the t backwards. Applied force upwards is 100. So there's different ways of doing it. I'm not going to do all of them, but cos of 30 degrees is equal to, and now 7.93 blah 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 times mass, which is 7. Okay, so if I go back here, you'll notice this one, I'm now going to make this one my memory stored, okay, so that I don't have to make rounding errors. Now this is going to be multiplied by 7, okay, which, no, I lie, let's divide by 7 again. Well, I made a mistake. So why did I memory store? Because I can memory recall. Cool. So that's going to be multiplied, not by 7, by 5. This is acceleration, and this is my mass. So not by 7, I'm working with the 5 kilogram, only the forces on the 5 kilogram. Because as you could see here, there was no T when I was working with the whole system. The system had T inside of it. It wasn't an effect on the outside. So that's why. And then so here I've got that times 5, and then plus, and now I'm going to add all of this. Now you'll notice if at the top I had just written down this value when I finished working it, or stored it somewhere in my calculator, I could have used it again. Now I'm going to have to add it again. So 5 times 9.8 times 0.5, because sine of 30 is 0.5. I didn't put in the 30, but that's fine. Plus 0.2 times 5 times 9.8 times 30 cos is equal to, and there we go, T 72.64. 72.64 Newton. The question was, will it break? It will. It will break. Okay, so as you can see, this was a massive sum. Well, massive, it's not really difficult, it's very standard. It's what you will, the type of question you will find in question 1, and you need to practice this. You need to be able to find the tension between two objects. So if you can see, we've got 14 minutes for that. With explanation, I think I went over a little bit. I spent 19 minutes on there, but I had 14 times 1.2, which gives me 17 minutes, 16 minutes. So I went up. Do you enjoy learning with video? Well, consider doing your matric with Elroy Academy. We've got online courses with video lectures and electronic exercises that you do right on your computer. It's automatically graded, so you get immediate feedback. But maybe you like to learn in an entirely different way. Then Elroy Academy is exactly for you. We have an assessment-only option where all we provide you is the assessments, and you can study for those assessments in any way you like. A way that's maybe different from the norm, like school.
a way that suits you. Whether teacher, tutor, textbook, heck, YouTube for all we care, as long as you pass your assessments. You see, school is not all about passing tests and passing grades. No, it's about learning, and we test your learning using assessments. So we'll take responsibility for the assessments, and you take responsibility for your learning. If you're interested in this, please go over to our website for more information. Anyways, thank you for watching. I hope you enjoyed it, and if you did, please like this video to encourage me to make more. Hope to see you in the next one.